you're so like, you
no sugar.
No sugar.
Yeah. But the thing is, like,
It's pretty sweet.
yeah, so recently, like, there was one place that sells bubble tea that was really, really popular again, and everybody loves it, but they stopped sending stuff here. They stopped delivering here.
Because it was just too much.
It doesn't make any sense, because people were ordering it every single
day. We have an entire.
So why don't we have a bubble tea dispenser on bar on campus?
I don't know if we make so much.
It would be convenient.
So they
Oh,
don't,
do they?
the crazy mango. So that's why they don't want anything to.
Okay, so I'm actually going to UWC Cheongshu on Friday to give this talk, so they'll see this title. And I wanted to practice on you, but I also would like to go into some more detail later on. This is supposed to be maybe a 30-minute talk max. So what it is at Davidson there's no graduate program. It's all undergraduate, liberal arts college, but undergraduates want to do research. Professors do research, everybody, thinks a lot. So this is a project that I started back like in 2008 with some colleagues at the University of North Carolina at Chapel Hill and Meredith College. And we talked about the spread of the HIV virus in the lymph system and applied a mathematical model to it, and then analyzed it mathematically to understand what was going on. So then Courtney wanted to do a project, and so I told her about this, and she said, oh, I'm really interested in Alzheimer's disease. And so we kind of morphed the setting, and then Savannah took that and found another application and wrote an honors thesis. She just graduated this past spring. So let me just kind of go through that progression, and then we'll do some examples and try to understand what's going on. So when you are infected with HIV, this is clinical data. And so what happens is you get an infection and you have an initial spike of virus. The dashed line stands for your healthy CD4 plus T cells, which help fight infection. And so in the first few weeks, you get this huge infection, and you may think you have a cold or something and you don't know, because the symptoms subside, the virus subsides, your immune system sort of dips, but then starts doing its job and kills off the virus. And then the scale changes from weeks to years. And so without drugs, there's a clinical latency period where your immune system is slowly weakening. The amount of virus, this is amount of virus in the blood, starts increasing. And when there is a lowering of the CD4 plus T cells, when your immune system is so weakened, opportunistic infections can happen, and that's when acquired immune deficiency symptoms take in. That's what AIDS is. So our model, when we did it, looked like this. So you can see a little dip, a spike in the infection. We played around with parameters. We looked up a lot of biology books to figure out what would be good parameters that actually fit clinical data. And these, again, are in weeks. So 300 weeks is about 6 years. And then once opportunistic infection sets in, then it's over. So, and now since that time, the treatments and the knowledge ahead of time, in particular right now, they have this new thing called pre-exposure prophylaxis. So people who work in high-risk areas can take medicine ahead of time. So the idea is either that you don't have very much infection, or it just doesn't make it through the barriers that your body already has in place to prevent the disease. Whoops. Don't know what that is. So here's basically the model. So what we do is we imagine there's a grid laid out on the lymph node. And so we sort of section it off, and the lymph node then has these cells or sites, and we mark each site as healthy, newly infected and highly infectious, infectious, and weakening infectious, because the HIV virus spreads out, but the cell it's using to duplicate dies eventually. So the cell weakens and it gets less infectious as you go on. So this stands for the progression of that virus weakening. And then this state 6 is what we call the depleted state. So the cell is just gone. In a healthy immune system, 6 would be replaced by a 0, because you would come back to a healthy cell. So 0 is healthy. But sometimes what happens is there are pockets where the HIV sort of hides out, and they don't know what causes it to reactivate. And so this 6 going to an infected site is what is supposed to mimic that. Or it could just say, yeah, I'm hanging out, I'm going to stay depleted and just not do anything for a while. And there are biological reasons why this model captures a lot of the effects of HIV. So since this is a grid, each site has 8 neighbors. And so what we do is each site gets updated simultaneously at the same time, depending on the neighbor's values. So if I have a 0, a healthy cell, I look at its 8 neighbors, and this 0, so this is all the different functions. The F1, F2, F3 stands for 6 going to 0, 1, or 6. But if you have a 0, 0 will always update to a 1 if any of its neighbors are a 1, 2, 3, 4. But it has to have more than 4 5s because the progression is weakened. And anything else, 1, 2, 3, 4, they just go up to the next one. And these represent 6 updating to 0, 1, or 6. So here's a little slice of the big grid. So let's suppose we had all healthy except 3 6s there. So this says I'm going to do F1, this says I'm going to do F2, and this says I'm going to do F3 to that one. How do we decide which to do? This is called a stochastic cellular automata. So basically you flip a coin and say, I think I'll use F1, I think I'll use F2, I think I'll use F3. The coin is not a fair coin. It's 0.998% of the time. 6 goes back to a 0. Your immune system's working. So that means that all the zeros stayed 0 because there's no 1, 2, 3, 4s around them. But the 6 goes to a 0, the 6 goes to a 1, and the 6 goes to a 6. Then the next time, I have this 1 here. So all these zeros around it are going to update to 1s. And since I colored that purple, this 6 is going to update to a 0. So all the zeros out here stayed 0, but you see these all updated to 1s. And this one, this is a 2 right here. Dang it. This is a 2 here. Here is a 2. And then that makes that a 3. Okay? And so you can see that the infection has spread just after a few time steps. And then here is a picture of a 700 by 700 grid. And light blue is there was a sprinkling of infection. After 5 time steps, you can see a lot of blue. So the color code, instead of writing 0, 1, 2, 3, 4, 5, and 6, it's white. No color is healthy. Light blue is 1, darker the blue, it progresses 2, 3, 4, 5, etc. Okay? And so what happens is the infection spreads rapidly, and then your immune system starts clearing it out, and you can see, if I zoom in, that there's some black there. Those are the 6s. And then 6s mostly go to 0s, but not all. And so you might get some sort of new infection starting.
So, like, do you write your own software? Or?
I used Mathematica to do this.
Oh, okay, okay.
And then you can imagine why the rings of infection go out, because of the 1s going to 2s, the 2s going to 3s. 6s mostly go to 0s. But occasionally, that 6 going to 1, that latent HIV that kicks in, might start this new spread. And once it reaches this, there's 1s everywhere, and that's when the number of healthy cells in that initial picture started declining. Okay? So this was like a 80-page paper, a lot of math in it, and even some eigenvectors in there. And then when Courtney was interested in doing some work, she was thinking about doing something more with graph theory. So a graph is a set of dots and edges that connect the dots if there's some relationship. So if I labeled these 1, 2, 3, 4, 5, 6, 7, 8, I may say 5 gets connected to 7 if these represent people and they had lunch together last week. So right now, I know that I've drawn an edge if 2 people had lunch together. 8, yeah. We had breakfast. If we had breakfast together last week. Oh, but nobody's just connected to 1, but that would be me. So now, right away, a bunch of information is encapsulated in this picture, right? You know that 4 and 6 didn't have lunch together. You know that 8 and 1 like to eat with other people a lot. Maybe a lot of people do. I guess a lot of them have 4, right? So there's a lot of information encapsulated. So why might we want to switch to graphs? Well, we wanted to look at the spread of Alzheimer's, how that worked. So we think of the brain as a giant graph, a neural network. And 2 nodes are connected if there's a pathway between them, right? If there's a synaptic firing that gets one to the other. You can simplify this picture. Different parts of the lobes are, different parts of the brain, the lobes are connected different ways. So you can simplify this in some way. And so the physical space is actually a brain. We label it. This is too big to imagine, right? We have a lot of neurons in the brain. And so we go over to the abstract, quote, topological space, which is just, we don't need the brain picture behind it. We just want those nodes and an edge if you can get from one to the other. So the way that we study that, instead of, so you see the disease progression occurs along these pathways, not by being next to a neighbor. You could have 2 neurons, one is very diseased and the other is very healthy, but there's no interaction between them, so it's not proximity, but availability of getting from one to the other. So that's why a graph was a good thing. And one time at a job interview, somebody mentioned this thing called zero forcing, and I was like, oh, what's that? And she said, oh, it's this graph theory thing, blah, blah, blah. So we looked it up, and we thought that it was really interesting, so we talked about that. Okay, so what is zero forcing? So I have a graph, and I put a color change rule on it. Namely, so let's say I have a graph that looks like that, and I fill a vertex. If a filled vertex has exactly one empty neighbor, then that filled vertex can fill the empty one. So there's no color change rule. I can't progress on this one because it has two neighbors, right? But if I had have filled those, now, if that was the initial setup, I could force this one, and that one would be colored.
Does it have to do something with this like very popular topic recently, like something like called fishing or firing, like this graph theory thing? Okay, I'll ask you
Let me
later.
think about it, yeah. So what we want to know is, so you can imagine that if you had a pathway that was, or a neuron that was bad, and it fired and spread some of these tau, beta, proteins that help spread Alzheimer's, then you can imagine that if there was a way to sort of fill out the whole graph, then that would be bad if we're talking about disease. So we call that zero forcing set is a subset of filled vertices, so that after you apply the color change rule, after a certain number of iterations, it fills all the vertices. And so the game that we play in graph theory with this CCR is, what's the minimal number that you can have, right? How is the minimum number of filled vertices so that the whole thing will eventually get filled under the color change rule. So that, we call that the zero forcing number, is the size of the smallest zero forcing set. So that's the minimum number it takes. And there are lots of different color change rules you could do. You could do a probabilistic one where you flip a coin, and even though you could fill it, maybe you will, maybe you won't. Maybe this is a really healthy cell over here, and it's just not going to be infected by that one, right? So let's just do a couple of examples. So this one. What if I filled that one? Couldn't do it. But what if I filled, let me erase that. What if I filled this one? So this is the original one.
That'll do it.
Then on the next step, I could fill that. And then on the next step, I could fill this, right?
Yeah.
Now I'm stuck.
Oh.
So this original one, so I'll just write it over here. This is not a zero forcing set.
It has to only have
Right?
one, like around.
It's not a zero forcing set because when I let it
the-
progress, it didn't fill out the whole thing.
that thing.
Okay, so let's see.
If
The
you start
problem
from-
was there. What
Start from
if
up there.
I did this one? Well, if that was my initial one, then after one step I could do this one, right? I'm stuck.
Oh.
So instead, maybe I will try those two. That works, right?
That works.
So if these two were at time 0, that's the initial forcing set, well, it is, then I could fill that one, and now I could fill that one, and then I could fill that one.
So
That's
what's
3.
the biological reason for you not being able to spread it if you have more than one?
So the idea is that those neurons fire one at a time, right? They don't, well, they do kind of go out, but the idea is that if you're going to spread disease, there's got to be something in the pathway that makes it up. That's another thing you could do, is say, oh, this is capable of doing more. So you could do K forcing and stuff like that. You can do more. Okay, so at the bottom of your sheet there, you have these. So why don't you, oh, here's a question. Is 2 the zero forcing number here?
Mm-hmm.
Yeah.
Was there any way, what if I did, Let's see, I got stuck. If I colored that one, I'm stuck.
Yeah.
Yeah.
It's
Yeah.
It looks like it's 2, doesn't it? Okay, so what about the graphs? The paths.
1.
These are called paths. This is called P5. It's a path because it just has you don't have any choice about where you go. You're just walking along a path. And you have 5 vertices, so that's a P5, as opposed to P5, which it is not. Okay.
1.
Yeah, 1.
It's 1, right? Okay, so an endpoint, right? An endpoint will force the whole path. So there's how many 0 forcing sets of size 1 are there?
2?
There's 2.
Both the endpoints.
How many of size 2?
2, 3, 3,
So
2, 3.
So I want to know how many 0 forcing sets are. So I want to put down 2 vertices. I want to fill in 2 vertices, and I want it to then be able to spread to the whole thing.
okay, so like
Okay.
1, 2, 3, 4.
8?
8.
How many?
9.
9?
Okay, we'll come back to that in a second.
1.
I promise. That's the end of the talk. Okay, so here are a couple of examples. These are 0 forcing sets. This
6.
one you have to have 2. This one you have to have 3. This is the complete graph on 4 vertices. So every vertex is connected to every other vertex.
Yeah.
So if I had, this is K4, if I had K5, K6, K7, you always have to have all but 1.
Oh, that's why making connections in your brain are better for like less.
Very connected, yeah.
Oh.
But you can't have too many or things can go wrong more. So those are called small world graphs, where there's a lot of connectivity, but not so much that you have a lot of redundancy. But you have to have some redundancy, because...
2, 3.
Okay, we're going to come back to that, I promise.
Or if it's 6.
Okay, so now I'd like you to, for this example here, I'd like you to try to find the 0 forcing number. Is that what I called it? The 0 forcing number for that graph. There's a lot of copies of it up here because I was going to talk about it some more, but I'm not going to. So. You have that one on there, right? Yeah. How come you guys have a green dot on yours? Oh, because I that's what I put on it. Sorry.
There's gotta be 4.
Yeah, I think it's 4 because you have
You've got
3.
the fully connected one.
Yes, it's 3 at least, and then
It's not 6. The previous one is not 6.
the previous one. But like, if you have an endpoint, then any of them works. So it's 4.
So what's the
If you have
minimum
this
number
one,
of vertices I
and
need to
one
fill
works.
so that it'll force the whole
Then
thing?
the endpoint works.
Yeah, the endpoint also works.
You don't have to start at the top.
That's
You
right.
can start in the middle, anywhere.
That's 2. That's 1. Okay.
That's
That's 9. Okay.
Good.
You think I should like make it closer by like turning it?
You can
Yeah,
do it with
let's
4,
zoom
right?
in on one of
Oh
those.
no!
You can
I
do it
don't
with
know
4,
how
but
to
can you do
zoom
it
in
with
in
3?
this camera. Oh, wait, does it capture in the?
Sometimes.
Hey, Cora.
Because it's more that you need to get into it one, not
Hey,
necessarily
Cora.
get out. So like, if you have a vertex
Your
that's
head is
connected
just
to
a
lot,
bit-
you probably don't
Sorry,
want
sorry,
that
No,
in
no,
your
it's okay, it's
vertex
okay, it's okay. Yeah, this is ideal. It's okay,
Because-
thank you.
It would be hard to get out of it. So for sure 4. Anybody get 3?
Sadly, no.
Do you think 3 is impossible?
Mm,
Did you get 3? So the problem is there's so much symmetry here, right? So if this is there and this is there, then if that was at 0, then this is at 1. I'll just put the 1 there. And now I'm stuck, right? So maybe if that one was also forced, was part of the zero forcing set,
I got 3.
then I could do
You got
this,
3?
but now this guy
Oh,
can't move, but this one can force there.
So that would
this
be
is
at
one,
time
this is
2,
force that one.
and now I
Then
can
this
split
one's
it time
forced
3. So
there.
it looks like
No,
it's
this one
3.
has 2.
3 is possible,
No, but
right?
this
In
one-
this case, because
This one's
this
filled,
can go
filled,
here,
this one's filled.
and then
Oh,
this
so you
closes,
go
so
from
this
Okay.
can go here.
Yeah.
to this one.
Yeah.
So there is 3, right?
There is 3, yeah.
Yeah.
So we have
Yeah,
some
'cause it
different
fills
ones,
out
but
this
by
one, so it takes away
symmetry,
that, and yeah.
so this is a zero forcing set. There.
Okay.
So basically, the time step doesn't matter in this case.
In this case, so that's another question you can ask. You can ask about propagation time.
Right.
Like, can you spread the forcing set out so that the propagation is quicker or slower? It's another question that people ask about this. And then here are a couple more examples, and I don't think I'll have time to do this, but let me just finish up. Okay. So then, Courtney did a lot of work on the zero forcing set and found out what, she connected it to brain graphs and this small world notion of a brain graph, and even experimented with some probabilistic stuff, wrote some code in Sage, which is Python, and came up with some nice results. Then Savannah saw this, and then when she was reading, she found out about this zero forcing polynomial. So what that does is it takes a graph, the notion of zero forcing, and associates to it a polynomial. This concept is only about 10 or 12 years old, so lots of stuff is unknown about it. So the zero forcing polynomial of a graph, G, with variable x, is just the number of zero forcing sets of size I times x to the I. So when I asked you how many zero forcing sets there were of size 2 for P5, the answer is 9. So for a path with n vertices, the polynomial is known, easy known. And so if you've taken stats or probability, this is the binomial coefficient. So n things take an I at a time, n minus I minus 1 take an I at a time. That's the formula for it. But if you plug in n equal 5 and let I equal 0, or not, well, I equal 0, how many zero forcing sets of there are of size 0? None, right? So no polynomial will start with a constant term. You can't zero force a polynomial a graph if you don't have a starting point, right? So now what I want you to do is confirm these coefficients. So we already got 2, right? You have to have either endpoint, and there are 2 choices of endpoints. The 9, how could we think about the 9? Well, I could take an end, I could do an end plus one other, right? Because once I have an end, I know I can zero force. And then the others just, so there are 4 ways to do that, right? Or I could do the other end plus 1, and there are 4 ways to do that.